Thanks for joining our Steidle Café this morning. So this is the last one this semester. And this semester, we've been celebrating the 115th anniversary of the Department of Material Science and Engineering at Penn State. And while last year was the 125th anniversary of our College of Earth and Mineral Sciences. In celebration of these two milestones, we have been hearing from a number of alumni who were named 125th anniversary fellows of our College of Earth and Mineral Sciences, and we'll hear from two more today. So today we have with us Dr. Stephanie Petrina Boyce and Dr. Jim Shebis. So we'll start with Dr. Boyce. She is the Principal Investigator, Department Manager at Paragon Space Development Corporation. She earned her BS from Virginia Tech and her MS and Ph.D. degrees from Penn State, all with degrees in material science and engineering. And she's now leveraging her polymer science expertise in several technical leadership roles at Paragon in direct support of NASA's Water Recovery Technology Roadmap, which is a critical component of enabling human travel into deep space. She's a PI for the Brine processor assembly, or BPA hardware, on the International Space Station. And for that, she supports all aspects of the on-orbit operation of BPA and guides the experimental plan in sustaining engineering for NASA. So thank you so much, Dr. Boyce, for being here today. We look forward to hearing from you.
Yeah, I wanted to start out. Thanks so much for having me again. I'm really excited to come back and talk to the department. I had such a great experience at Penn State. Really shaped my formative years, such a great education in the Department of Material Science. So I'm just really excited about the opportunity to come back and talk about where that has taken me in my career since my time there. So I'm originally from Richmond, Virginia. And as was mentioned, I got my bachelor's from Virginia Tech, my master's and PhD from Penn State and Michael Hickner's group. So I was mentioning to Allison before the call, I was Michael Hickner's one of his first two students back in 2007. So it's hard to imagine that much time has passed. But yeah, it was a great time at Penn State, and I certainly learned a lot. So I wanted to talk a little bit about, just mostly for the students, about sort of the career path that materials have taken me on. It's been a bit of a tortuous one, as you'll see from my presentation today. So after my PhD, I went into, I was just looking for a job. Wasn't really interested in staying in academia. I really wanted to do applied research. And so I was looking to work in private industry. And I went to Georgia Pacific, which is actually a paper manufacturer, the largest manufacturer of towel tissue napkin products in North America. So I spent about 7 years working at their R&D center in Neenah, Wisconsin. That was a really fun job. I got to do a lot of different stuff. So, you know, my background at Penn State was in polymer science, which is one of the things that I really appreciated about materials and that drew me to it in the first place is that you know, the fundamental nature of the technology. Materials apply to everything. Many technologies are dependent on materials performing their job. So it wasn't, you know, learning about paper science was something I had to do, but I got to do a lot of fiber research in my time at Georgia Pacific. And, you know, cellulose is the most abundant natural biopolymer. So that's how I kind of thought of my work. That was a really neat balance of long-term research. I got to do a lot of commercial manufacturing support. So like a commercial paper tissue machine, if you actually take a moment to think about how paper is made, I mean, it's a web that's extremely thin, flat, not wrinkling. And it's made of completely natural fibers. So it's actually quite an amazing technology to see an industrial paper machine operate. And so that was a fun job. It was a mix of new to world research, manufacturing support. I got to do a lot of different fun things. And so in my last year and a half at Georgia Pacific, I was actually the principal product developer for Quilted Northern Ultra Soft and Strong toilet paper. And so one of the things that I also did was a lot of sustainability research and how consumers perceive sustainability. We actually had a proprietary method that we had developed internally at my company for making paper products that used less water and energy. And so one of the exciting things I got to do was that product was rebranded about a year ago. And so I show the packaging here. So I actually worked with our business development team, our marketing team, to understand what's important to consumers, what do they care about, what can we honestly say about our product where we're not greenwashing, being very truthful and upfront about how it's made. But still, there was a hole in the market for sustainable but high quality products. So it was really neat to get to sort of work on the soft side of understanding what people want, and then applying my technical background to being able to actually deliver that product, because we were also doing some performance enhancement work at the same time. So that was really fun. I was there until June 2020, which is, so I was there for the beginning of the great shortage of 2020, which people have questions about that. That was a very interesting experience, but it was just kind of ironic because I was surrounded by toilet paper. So I had no lack of toilet paper. And I mailed some toilet paper to one of my old group mates from Penn State, who was literally buying black market toilet paper for $10 a roll. I was like, nope, I will send you some. Please take this. So after, so looking for a change, leaving Georgia Pacific and coming to Paragon, which is where I'll spend the rest of my time chatting about today. So again, I was in Wisconsin for Georgia Pacific, which, not originally from there. It got a little old after a while. So now I live in Denver. And actually, we have the two-body problem because my husband is also a graduate of Penn State Material Science. And so he, had a job opportunity in Denver. Definitely a place we wanted to live. So that's where we are now. And so I looked for new opportunities in Denver, a lot of things in the commercial military, defense, aerospace. So I knew, okay, now I will have to apply my materials background to one of these fields, not a problem. So I was hired on at Paragon in June 2020, because I had a solid academic background and employment. I, went straight from one job to the other. So feel very lucky about that. So I started out in a materials and process role for essentially a life support system for the Lunar Gateway, which is the new space station that is being built by NASA to orbit the moon. But still looking for opportunities, with my PhD and background, like we knew that I would be more of a technical lead role. So when those opportunities came up, I jumped on them, and that was when I became a principal investigator. Still principal investigator for 3 different programs, as well as then in December, I became the department manager for PI. So, just wearing all the hats still, but I don't like to say no to new opportunities. So that's where that gets you. So I was also asked a favorite Penn State memory. And what I'm going to say is probably the recruitment weekend for material science department. Because what I didn't know at the time was that I met my future husband that day. And so the funny thing is I didn't even talk to him because I was so focused on like, who will I work for? Do I want to go here? All that stuff. So yeah, married a person from the department, Josh Boyce, who graduated from Dr. Hellman's group. So thanks, material science, because you've formed my life in many different ways. Also, not that you can tell from this view, but I am also 32 weeks pregnant with our first child. So exciting times for in our life. Okay, so let me talk briefly about Paragon and what we do. So at my current company, we keep people alive in space. So if you imagine people are in a capsule being sent to space. It's like a thermos where there's no air exchange. You're going into the vacuum of space. Materials play a huge role in keeping people alive in an area where there's no air exchange with the outside. We need to remove humidity so it doesn't condense on electronics because people are constantly perspiring and respiring. And that's actually where my material comes in. You need to do trace contaminant control, removing impurities from the air. Thermal control, obviously in the vacuum of space. When the sun is shining on one side of an object and not on the other side, there's a huge thermal difference in what those materials are experiencing. And so the company that I work for now, Paragon Space Development, focuses on specifically ECLIS systems, which are environmental control and life support systems for space. So relatively small company. When I joined almost 2 years ago, it was about 70 employees. Now we're about 250. So, you know, as the commercial spaceflight market really expands very rapidly, there are a lot of opportunities, and essentially, like, you know, tourism to space and keeping people alive as they spend time in space is becoming a really critical future need. So just a lot of business is just naturally coming our way. Yeah, so I just wanted to, I picked a few websites, you know, Orbital Reef. A lot of people with deep pockets are just want to go see the next frontier, want to go see space for themselves. So there's just really a lot of new opportunities that are opening up between Orbital Reef, Virgin Galactic, SpaceX. So there's a lot of need for keeping people alive in space, right? So as was mentioned in the very beginning, one of the technologies that I support is the Brine processor assembly. So very ironically, I used to work on toilet paper. Now I kind of work on toilets in space. And so this particular device that my company invented, it actually, we received processed urine from on orbit. So in space, one of NASA's critical missions to be able to enable human space flight to deeper space is that we have to close the water recovery loop to 98%. So you aren't throwing anything away. It's very expensive to launch things out of Earth orbit into space. And so we need to recover the water from, so on ISS, they're always recovering water from the air that people respire and perspire. But urine is a huge source of water that can't be ignored. And so on the ISS, they actually have a urine processor assembly that recovers up to 90% of the water. And then now our device actually receives that pre-processed urine, which is now concentrated, and then recovers another 90+% of the available water from that. So we have actually demonstrated with our device, like we get telemetry back from on orbit and then analyze the temperatures essentially to be able to identify how much water we've removed. So it's very exciting times for the Brine processor because actually NASA is now at the point of over 98% water recovery because of the Brine processor assembly. So we are patiently awaiting that that disclosure, but it's been very interesting, exciting to be a part of it. So very briefly, how the Brine processor assembly works. It is essentially a very fancy box where air is taken in on the left side, drawn in by a fan. This soft goods material in the middle, we actually call a detruser. Within that is placed a bladder that is filled with urine brine that's processed on station. So we receive this pre-processed brine, air is drawn over it. It's put in the bladder is a semi-permeable membrane. So funny enough, the material that it's made out of is an ionomer material that I studied for my PhD work at Penn State. So it's used in hydrogen fuel cells, but it's also applied here because it's very selectively permeable to water. And so in this case, what we're doing is we're essentially blowing warm air over this urine brine, and the inner and outer layer of this bladder that our company developed actually very selectively allow exclusively water to evaporate, retaining all the solids and liquids. And the majority of the contaminants, we have something like 5 to 7 orders of magnitude more water collected than contaminants. So very, very high water recovery rate. And so it just removes this, blows it out into cabin air, and then their current systems on orbit actually recover the humidity from the cabin air. And in this very grainy picture that I took from the ISS website, where that I've cited below. So I have some cool on-orbit pictures of this in operation, but I didn't want to have to, it's a lot to ask NASA for approval to use their pictures with astronauts in it. And so I was like, okay, well, here's what's publicly available. So sorry you don't get some cool astronaut pictures floating around, but we've seen some really neat things on orbit. So if you want to learn more about it, you can Google the Brine processor assembly, but this is its location in node 3 of the ISS, which is one of the habitable modules. It's very close to the toilet because obviously we don't want very long hoses extending around to be able to transfer brine between the urine processor assembly and their recycle tank filter assembly. So all very centrally located in that node 3 on the ISS. But this is, you know, a very essential technology. It's been really neat to work on it. It's so funny to come back and like remember all the things that I used to know about Nafion from graduate school, and you know, bring that all back to be able to improve this technology, support its operation on orbit, and be involved with such a critical piece of enabling human spaceflight to deeper space. So, for example, for humans to get to Mars, we need to have this high level of water recovery. So yeah, a lot of people inquiring about the technology and how they can customize it for their particular needs on, you know, all these future commercial space stations. So that was what I brought to talk to you about today, and I would be happy to answer any questions.
Stephanie, that was really wonderful. You know, I think very often when people think about space flight, recovery of water is maybe not top of their list, but as you indicated, it's extremely important. I wanted to ask on behalf of students, if students are interested in becoming involved in technologies supporting spaceflight or supporting NASA or any of the other you know, SpaceX and the like, what's the best pathway for a student to prepare for a career in this field?
Good question. So I was actually thinking about this because, you know, I would have never considered anything like this during my time at Penn State. There are NASA fellowships that can be applied for, and even NASA internships. And I can try to look up some of that information and share it with you. But, you know, for somebody to just Google NASA fellowships and trying to get that initial foot in the door of exposure to NASA, getting to work at their various sites, that's the best way, I would say, to sort of get your foot in the door. I mean, we're a smaller company. We do have some internships, but people generally like to see some experience in spaceflight, some experience with, you know, different spaceflight, I guess, applications. So I don't know, maybe sort of an exception because the particular material I happen to work on is exactly what we do here. But in general, I would look for those opportunities through NASA to get your foot in the door. There's certainly, I mean, and if you're near graduation, you can certainly look for just going direct through, you know, all these companies are hiring now. I have to say, it would be great for people to look for those types of internship opportunities or getting your foot in the door with NASA, because we're at a point of extreme growth right now in the industry. That doesn't mean that people with these backgrounds are available to hire. So there is sort of a lot of competition in commercial space flight right now, because everyone is trying to develop their own technology, develop their own hardware, and there just aren't the employees there with experience because the industry is growing very, very rapidly. So that's where I would at least start out. But these companies are going to be recruiting very heavily in the future. I mean, already are.
Thank you. Good to know.
Great, thanks. And to those of you in the audience, if you have a question, you can either type it in the chat or use the raise hand feature, and then we'll ask you to unmute. So I had a question. So you're PI for a number of efforts related to space technology, and I was curious if you could talk a little bit about the process for developing those products and testing them on Earth, and then making sure that they work in space.
Yeah, that was, I'm not going to lie, you know, coming to a different, so I've been in many roles in my career path, and changing to aerospace was challenging. Totally different industry, extremely rigorous requirements that have to be met, as you can imagine, right? And so it's an extremely regimented process of designing, doing the analysis to ensure that your system design works, actually manufacturing, building, and testing. So in a principal investigator role, you're the technical lead for a program where you are overseeing, you know, a design engineer, an analyst, a manufacturing engineer, a test engineer, and shepherding the technology through the entire process. So that's one of the kind of cool and unique things about the company that I work for now. We do very fundamental engineering. There's not many places that do that anymore. And so on one of my other projects, we're actually building another device and testing it right now to extract water, again, from human waste, because that's just going to be a critical technology for future human spaceflight. It is, I don't know what else to say about it. It's extremely rigorous, the oversight that has to go into it, the documentation, lots of documentation. But it's really like, it's kind of amazing, because we are developing something that never existed before, from an idea, a concept. Sometimes we get NASA small business grants based on what they're interested in doing, and we say, I think we can do that. Like, these are their future needs. And so yeah, it's a whole process. But that's actually how the Brine processor assembly was even invented in the first place, from just an initial NASA small business grant. So you can imagine, now that it's spaceflight hardware, it's been through many, many iterations of tests to prove that it will not only work on a ground environment, but in microgravity. And that's where we have a lot of analysts as well, who you know, understand you know, a lot of like shock and vibe. Can this survive a launch environment? I mean, it's a long list of boxes you have to check to be able to qualify spaceflight hardware. It is a long list.
Okay, great. Thank you. And our next speaker will join us around 10:30. So there is time for questions.
So I had a follow-on question. I mean, we you know, back when I was a kid, we learned that, you know, Velcro and Tang were developed for the space program and then migrated into everyday life. I don't know if Tang is still around. I haven't seen it in a while, but I was just wondering, to what extent do technologies developed for space life make their way into terrestrial use? And I was thinking of desalination, for example. Is the technologies you're developing, could they be applied there? And are there plans to do that?
So yes, we are always looking for other opportunities to apply these types of technologies. And I mean, it's a long list of things that we learn in a microgravity environment. I mean, they're constantly doing experiments on the International Space Station. It's funny because to understand the effects of microgravity, essentially it's 10% reduced gravity in low Earth orbit, where the ISS, you know, orbits the Earth. But that's reduced enough to where people float in space. That's what you're seeing, people, you know, floating around in microgravity. And so just understanding how the absence of gravity affects the properties of a test. They do a lot of biological experiments. So yes, they're constant. It's funny because we always have to, you know, whenever we're performing a function on the Brine processor, like changing out a bladder, for example, we have to like schedule astronaut time because their days are completely scheduled. They're very busy, and it's hard to be able to shuffle, you know, that work around to kind of keep things on target. But to get back to your original question, so obviously water, there are a lot of places, you know, we're very privileged in the United States to have access to clean water all the time. There are plenty of places that absolutely do not on Earth, right? And so that is somewhat of an area that we considered, of course, like because this technology is so very specific, and again, we have to pass a lot of requirements for design pressure, for operational conditions. Developing this hardware is extremely expensive. And so, you know, water is more available in terrestrial applications to where they're not, you know, this very specific technology isn't needed. But we have considered leveraging this in other ways for water purification opportunities. We just have so much going on in terms of people wanting this for space applications right now, that's where we're primarily focused, but it's definitely on the radar of like, where else in terrestrial applications could we leverage this technology? Just people want to pay us for this technology now to develop it for their, you know, their commercial space station. So that's where we live.
Great, thank you.
Great, thanks so much. That was really neat to see, and very informative, and nice hearing about your journey. So thank you so much for your presentation today. We have our second speaker here as well. So thanks, Stephanie.
Yeah, thanks for the opportunity.
Yeah. All right, so thank you so much. Our next speaker is Dr. Jim Shibitz. Sorry, he's the head of the Propulsion Science section at Oak Ridge National Laboratory. He received his Ph.D. from Penn State in fuel science in 2005, and then he joined Oak Ridge National Laboratory as a postdoc. In particular, he joined Oak Ridge to pursue a career to reduce the environmental impact of vehicle transportation by advancing the use of bio-based fuels, making engines more efficient, and reducing the criteria pollutants from engines. His research interests center around developing a better understanding of engine and fuel interactions, particularly with the utilization of alternative biofuels and low life cycle carbon fuels. So thanks so much for joining us today. The floor is yours.
Well, thanks so much. I really appreciate the invitation and the opportunity to come here today. So I figured I would talk a little bit about my journey here and also about a career at a national laboratory, because when I was a student at Penn State, I didn't know that much, and circumstances led me here. But I think it's a good career to hear about So I'll just talk about my own timeline a little bit. I was at Penn State for a long time. I lived in State College for almost a decade. I did my undergrad in chemical engineering there, started in 1995. That followed by a master's and Ph.D. in fuel science. At the time I was doing my chemical engineering undergrad, there were certain focus areas, and one of those was energy and fuels, and that connected me with Andre Bayman, who was a professor in earth and mineral science at the time, and I did my graduate school work in the Energy Institute there. So that was a really fortuitous connection, and I found that I really had a passion for trying to improve the environmental footprint of energy technologies, particularly transportation. So that's what I did my master's and PhD work in there. Had a great time. And then around the same time I graduated with my PhD, I got married. That's my wife, Angelique. She actually just got the Charles L. Hostler Award. We were in State College this past weekend. She's actually still there, meeting with different folks. And right at that time, I joined Oak Ridge National Laboratory as a postdoc. I had some experience during my master's coming down to Oak Ridge, which is how I got connected. And then I joined the ORNL research staff in 2007. Spent a lot of time doing a lot of different research activities. A lot of it's been focused on alternative fuels. Some of the work that I did at Oak Ridge National Lab was cited by EPA in their rulemaking process to make E15 a legal motor fuel. And I've had similar sort of high-level impacts with biodiesel as well. And then just through my life, that's my first child, Seth. He's 14 now. My daughter, Sophia, she's 12. And then sort of in the 2015 type timeframe, I got involved in taking on some higher level leadership roles within DOE consortia. So the co-optimization of fuels and engines, or co-optima, was a program that I had a leadership role in, and it was a roughly a $12 million per year funded effort from Vehicle Technologies and $12 million from Bioenergy Technologies Office at DOE. So overall, about a $25 million program, 9 national laboratories taking part in it. So it was a large effort, and we did a lot of great work. I also had a leadership role in another consortium. It's a bit smaller, about 5 national laboratories working together to develop better fundamental understanding and modeling tools for engines and combustion. And then in 2020, I became section head of ORNL, section head. So this is a layer of management in between group leader and division director. So up until this point, I had been an individual contributor for my whole career. But then all of a sudden I was managing managers or managing group leaders. So it was quite a step up. Well, it was quite a step. I'm not sure if it was up or down or sideways, but it was quite a step, and still adjusting to it honestly. But at the same time, the whole sort of portfolio of technologies I've worked on is changing dramatically. DOE is not focused on biofuels for ground transportation anymore, at least not on highway ground transportation. In their mind, that's a fully electrified sector. So we're shifting towards the hard to electrify parts of the portfolio. So that's off-road, marine, and possibly some aviation, which is not an area that DOE has typically worked in. So I'll say a couple of words about national labs. National labs exist somewhere in between the space that industry occupies and academia occupies. So national labs are similar to academia in that publications and publication metrics are really important to your advancement here. It is the research product. We don't sell consumer goods, so that's that is our research product. That's what we get out there, writing proposals and getting grants to do funding or just maintaining those relationships with our DOE sponsors is very important. And we also tend to work on lower TRL or technology readiness level types of technologies here at national labs. So that's similar to academia, but it's similar to industry in that we tend to do a lot of large scale team science with a lot of different investigators and a lot of cross-cutting expertise. And that's something that often is not possible with the size of the grants that you get in academia. So we can say pull off larger scale projects at national labs. We also work with a lot of industry partnerships, particularly in the part of the national lab that I'm working in, which is very much on the applied side. But in some ways, we're unique from both industry and academia in that we have some of the world's most powerful science tools. Oak Ridge National Lab, well, who has the fastest computer in the world changes seemingly on a week-to-week basis, but Oak Ridge has held that title probably 4 times since I've been here. And we're going to have the first exascale high-performance computing machine in the world. I think that's due to be commissioned next year. We have 2 of the world's most powerful neutron sources. One is a nuclear reactor, a high flux isotope reactor, or HIFER. Another is a pulsed source called the spallation neutron source. So there's you can do a lot with neutrons, anything from imaging. So unlike X-rays, where a dense matter is more difficult to get through, a lot of metals are almost invisible to neutrons, but you can see hydrogen containing things very well. You can also do diffractometry with neutrons at a large scale. X-ray science, ORNL does not have a synchrotron neutron X-ray source, but other national labs do. Oregon National Lab, for instance, has their advanced photon source. So they've done a lot with X-ray science, materials development and characterization as well. So lots of unique science tools. And I'll just say, I have a couple of slides about ORNL. In particular, it evolved from the World War II Manhattan Project, as did the whole of the National Lab complex. Was 3 separate facilities. And this was the facility that you're looking at was the first sustained nuclear reaction, took place here at Oak Ridge National Lab. That first site is actually still a museum that you can go and visit. So they've turned it into an on-site museum, but you can see how big the campus has grown around where we started from. And then there are a couple of off-site buildings. I work at the Hardin Valley campus, and that's 15 miles off of the main campus or so. And that campus is where most of the transportation research takes place. And then there's the spallation neutron source. This is the powerful neutron source, the most powerful pulse neutron source in the world. So ORNL's mission is to deliver scientific discovery and technical breakthroughs that support DOE's mission in clean energy and global security. And I think they're going to add decarbonization to this overall mission as well. And I listed some of these earlier, but signature strengths in computations, material science, neutron science, as well as nuclear science and engineering. And just a couple of claims to fame to show you the sort of scope of what we do. ORNL had, it's now over $2 billion in expenditures. This is the FY19 number. We have over 5,000 employees. There's been a lot of research guests. It was 3,200 annually before the pandemic. That went down to almost 0, and now it's starting to ramp back up again. We have the nation's most diverse energy portfolio and nation's largest materials portfolio, which I think is hopefully interesting to this group. So I guess anecdotally, one of the things that I wanted to say is when you're looking for higher temperature aluminum alloys, the materials team at ORNL did a lot of computing work with with the high performance computing and develop some high temperature aluminum alloys that are already in production in terms of building engines and casting engines. That technology was licensed to FCA, which is now Stellantis. So we can see things that we work on go from concept to proof of principle to commercialization, which is really exciting. Like I said, journal articles are our primary output. In calendar year 2018, we had over 2,300 published journal articles, patents, inventions, disclosures, and licenses. And I'll just leave by saying this most recent addition to the periodic table, Tennessean, is an element that was actually invented in a nuclear reactor at Oak Ridge National Lab. It's not a naturally occurring element, so it has a very short lifespan. Hopefully I made some of you curious about what happens at a national lab. So I'll open it up for questions.
Great, thank you so much. Again, if you have questions, you can go ahead and type those in the chat or raise your hand to ask to be unmuted.
So Jim, a very nice presentation. Thank you. I was wondering about the emphasis on, well, energy is, you know, when Oak Ridge was first developed, energy wasn't the focus, or at least not the kind of energy the way we, you know, for domestic use, right? Energy in a different form. So I wonder if you could speak globally about where you see the lab going in terms of energy and you know, energy storage and enabling renewable energy and so on.
Yeah, so that's a good question. So the Department of Energy has a lot of different offices, a lot of different parts to it. One of the parts that you don't hear a lot is about how DOE manages the nuclear stockpile for the country. That is, there's some nuclear and national security work at this lab, but they have other facilities that are really dedicated to that. So adjacent to us, there's Y12, which is one of the repositories for the nation's nuclear stockpile. There's another one up in Washington State. So that's actually a big piece of what DOE does. DOE then has their Office of Science. They also have their, and I get pretty much all of my funding through EERE, which is Energy Efficiency and Renewable Energy. And that's the part of DOE that's really focused on renewable energy. And DOE ultimately, though, is it's an executive branch part of the government. And its priorities reflect what the administration's priorities are. So this administration, excuse me, has decarbonization as the #1 goal, and you've seen that in a lot of messaging and a lot of the research priorities. The goals are centered around decarbonization. Different national labs have different pieces of that overall pie. The National Renewable Energy Laboratory is actually an EERE laboratory. Oak Ridge National Lab is an Office of Science laboratory, although work gets shuffled between the labs. So the wind and solar parts of the portfolio are mainly at NREL. At Oak Ridge National Lab, we do a lot with vehicle electrification, wireless charging. We have a large battery portfolio here at ORNL, which is one of the major barriers for more widespread vehicle electrification. We also do a lot with smart grid technology and managing the grid. Energy storage is a huge challenge, and I think people are trying to work on that from different angles. Batteries play into that, but so do other types of things. DOE has launched a number of Earth shots. You may have heard some of these. There's the hydrogen Earth shot, where they're trying to get to $1 for 1 kilogram of hydrogen and there's a carbon footprint associated with that that's very, very low. And then there's a CO2 Earth shot that's centered around stably storing CO2, removing it from the atmosphere and stably storing it. And then there's also an energy storage Earth shot. Those are actually in the process of being awarded. There's going to be a lot of new awards and new centers that come out of those. But a lot of those are focused on getting things closer to deployment. And that's another thing this administration is doing. There's a lot of large investments, but a lot of those are not in fundamental research. A lot of those are in demonstration and deployment types of activities. Did I answer your question?
Yeah, very much so. Yeah, thank you very much.
Thanks. And we got a question in the chat, which thanks you for your talk, and says, within a national lab, is the main option for career advancement a transition into leadership roles and away from hands-on technical work? And the second part of the question is, have you enjoyed your new management role?
So to answer your question, no, transitioning to leadership roles is not, it's something that's there, and it's something that I resisted for a large part of my career, and it was only part of a reorganization and 5 separate conversations with my leadership convincing me to go into that. Have I enjoyed my new management role? That's kind of a loaded question. Yes and no. There are certainly things that I enjoy about that. In being in the management side of things, you have more influence on where you're going programmatically and what types of things are important, and an ability to influence internal investments and lab priorities and things like that. But I do miss going into the laboratory and doing work myself, having the time to write the papers. I'd been at Oak Ridge National Lab for over 15 years, going on 20 years. I certainly wouldn't have wanted to go in this direction before that point in my career, and maybe I did it 5 years too soon. I don't know, but I think there's maybe I'll be in this role for a while, and 5 years from now, I'll go back to the lab and spend the rest of my career doing the hands-on laboratory work and writing papers. That's stuff that I really do enjoy.
Great, thank you. And then I have a question, which was, if you could just talk a little bit about the pathways for graduate students to explore opportunities at national labs, both during graduate school and then after graduate school, so how they can kind of get involved. Yeah.
So Oak Ridge National Lab does have a large internship program. It actually starts with undergrads and then through graduate students. I can forward that link to the page with you. Through the pandemic and then through some reorganization of those internship programs, I don't have a great feel on what all the opportunities are, but through a separate initiative, I'm working on trying to get a better handle on that. So I can extend those to you, but I would certainly be happy if anyone wants to reach out to me directly. I'd be happy to try to put you in touch with the right person. But then we have a lot of postdoc type of opportunities here. I'm assuming that a lot of people are familiar with how postdocs work, but it's professional employment, but it's also a temporary position within the part of the lab that I work in. I was a postdoc here before I was hired onto staff, and the same is true of many of the folks that I work with here at ORNL. So that is a pathway to full-time employment. I know a lot of organizations don't treat it that way. A lot of people don't hire staff directly from their postdoc pool, but we tend to use that as a really long extended job interview so that we are hiring known quantities, and that's worked out really well for us.
Great. All right. Well, thank you so much. So I want to say thank you to Stephanie and Jim for your time today and your insights that you shared with us. Thank you also to our audience who joined live, as well as those that have watched online later. And as I mentioned earlier, this is our last Steidle Café of the semester. So thanks everyone for coming, and we'll see you next semester.